Okay, this next example, well, this is Notes 5.3 Part 3. In this next example, we're going to compare potassium with calcium. And if you look, potassium definitely has a larger atomic radii than calcium. Calcium also has more electrons than potassium, so what gives? Well, the key to understanding this is it's not the number of electrons as you go across the periodic table that determines the size or the rate of the radius, but rather it's the number of protons. It's the number of protons. So let's have a look and see how we can explain this trend here. Okay, let's go ahead and do our configurations. In this case, for potassium, we have 19 protons and 19 electrons. And our electron configuration is 1s2, 2s2, 2p6, 3s2, I'm sorry, 3s, yeah, that's right, 3s2, 3p6, and 4s1. Okay, 4s1. Same thing here for this one, except we have an extra electron, don't we? We've got 20 protons, 20 electrons. So we're going to draw this whole thing out, and we're going to end on 4s2. Let's do it. 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. Okay, so we've got that extra proton. That extra proton is adding extra strength to the positive charge in the nucleus. Okay, so let's look at the atomic radii of each. For potassium, atomic radius is 227. And for calcium, the atomic radius is 197. The ionization energy, the amount of energy required to strip this electron away, for potassium is 496, and for calcium it's 419. So it's got less ionization energy, right? Okay, so let's go ahead and explain this. Both calcium and potassium have outer electrons in the fourth shell, but because calcium has more protons than potassium, its outer electrons is more attracted to the nucleus and requires more energy to remove. As a result, calcium has a smaller radius and a higher ionization energy. Okay? Calcium has a smaller radius and a higher ionization energy. You know what? These two should be switched here. That's wrong. I knew something seemed wrong to me whenever I said it. That didn't make any sense. This should be switched. Okay? Calcium has a higher ionization energy than potassium. These numbers are incorrect. They should be switched. Okay, next. Going across a period, the number of protons increases, so the outer electrons are more attracted to the nucleus and are more difficult to remove. As a result, the atomic radius decreases and the ionization energy increases. Yeah. So I want to be very clear. This is a typo that I just now spotted myself. Okay, ionization energy for, let me just cross it out. Jeez. That should be 419, 419, and this one is 496. Okay? Yeah, be very careful about that. The ionization energy increases as you move across the periodic table because the strength of this nucleus, the protons in the nucleus, there's more of them, so that positive strength increases. Okay, that requires more energy to remove that electron. Okay, the last part now is the explanations for ionic radii. So ionic, remember what ions are. Ions either means you're taking an electron away or you're adding an electron. Two. So in this case, lithium, sodium, potassium, and rubidium, they're all +1, which means we've removed one electron. So let's go ahead and draw the ion versus the neutral atom, and I think it's going to be very self-explanatory. And using a little common sense, you should be able to figure this out no problem. So lithium, that's regular lithium. It's got 3 protons in it, okay? And then over here, we'll do lithium plus, okay, and that's got, the number of protons is 2, Okay, so that equals 3 and this equals 2. So let's go ahead and draw this one first. I'll try to draw this the same size, relatively speaking. Okay, so if it's got 3 protons, that means it's going to have, if this one is neutral, it's going to have 1, 2, 3 protons. This one, sorry, that's also got 3 protons. That's also got 3 protons, but it's missing 1 electron. It's missing 1 electron, okay? So it's got a positive charge here, which means it's missing an electron here. I'll do it like this. Okay, that's what you have to consider. That's got no charge there, which means it's got all 3 of its electrons. This one is missing an electron. So look what happens. Okay, look what happens. Now we only have this one shell here surrounding the nucleus versus, okay? So what happens is this atomic radii actually decreases. The atomic radii decreases, and that's the same all the way across. Look, okay? Here's neutral atom versus if we've lost an electron, the radius decreases, like so, all the way across. Okay? So here's what we can say about that trend. We can say, in the case of sodium, both have 11 protons, but sodium cation has fewer electrons than sodium, so there are less repulsion between electrons, resulting in a smaller radius. The radius decreases when electrons are removed, okay? You know what? You can just say that right there if you want. If you feel like that's too confusing, leave it out. And you can just say radius decreases when electrons are removed. Right? Radius decreases when electrons are removed. And now let's look at the next one. The next one is the anions, which is a negative ion of chlorine versus Cl minus. I'm going to, in the notes it says Cl versus Cl minus. I'm going to go ahead and use F versus F minus because it's easier to draw. Here's F, fluorine. Okay, we've got that empty seat there. We need 1 more electron to make this complete. Well, what happens if I were to add another electron into this shell? Well, what happens is I start to, although it becomes more stable, I've got more electrons in the shell, and each one of those electrons has a negative charge, correct? So if I were to add 1 more electron here, and all of these electrons now have negative charges, what's going on is there's more negative charges interacting with each other. And what do like charges do? They repel each other. So because there's more negative charges in this shell within close proximity to one another, what happens is this radius of the atom will actually expand a little bit. It will expand. So that's why you see this trend here. So F, very small radii, but if I add 1 more electron, then it gets way bigger. Why? Because these electrons are interacting with each other, and they all have a negative charge. And that trend continues for all of these radii. So here's what we can say, something to this effect. We can say something to the following effect. Both have 17 protons. Cl minus has more electrons than Cl, so there are more repulsions between the electrons, resulting in a larger radius. Oops, I'll say it one more time, sorry. Both have 17 protons. Cl minus has more electrons than Cl, so there are more repulsions between electrons, resulting in a larger radius. Okay? The radius increases when electrons are added. I mean, you could just remember that. That's the trend. That's the explanation. I would write them both down if I were you. I would write them both down. I don't think that we're going to address this second part down here. All right, so I'm going to go ahead and leave that off. I'll leave that off, and then this is all you need to know about the trends and the explanations. Okay, that concludes part 3 of the notes.